Good morning, everybody. Good morning. I'm Joanne Britton, and I'm very happy to welcome you to our bucket class this morning. Before we get started, please remember to turn on your T-coil if that applies to you. And please turn off your cell phones and put them away so we can all pay attention and enjoy the class today. This morning we're very happy to welcome Ben Guenther, who has been sitting where you all are for a long time here. But today he's up here in the front, ready to share some of what he's learned in his 27 years working for NASA about wind tunnels. So we're all eager to learn, Ben. Welcome.
Thank you. Can everybody hear me in the back? Is that fine? Okay. Yeah, thumbs up. That's good. All right. This is the... Oh, I hope everybody had a chance to read the paperwork, the notes, because that's to give you a good thumbnail sketch of the history and things like that, as well as a timeline. This is Langley Field in the latter part of 1917, and let's see, right here you have a building, and that is Building 58. This is the first building that NACA built. Anybody would hazard a guess what that would be for a government organization?
Administration.
Exactly. No, he got it right. He was first. Admin building. Yes. Here it is again. And this is Building 60. We'll talk about that in a few minutes. This is in the early part of 18. It's a two-story building, rather nicely done. Whoops, go back. All right. The first floor was all offices, had a small cafeteria and restrooms. The second floor was actually for the trades. You had a pattern maker, woodworkers, you had a small machine shop, you had draftsmen's tables and things like that. They also have a photo lab on the second floor. Now, in about 4 to 5 years, they would end up building a separate building, and the trades would go into that, and offices would end up going up into the second floor. Now, this is Building 60. It would contain, or house, I should say, the very first tunnel that NACA had. And it was called the 5-foot atmospheric wind tunnel. It actually, the purpose of this tunnel was simply to train the inexperienced NASA personnel, the engineers, in how to operate a tunnel, how to gather the information, how to process it, so they could be used. At the time, only Stanford and MIT were graduating aeronautical engineers, and there weren't many jobs for them, and they had very little experience other than working at a few small tunnels that Stanford and MIT had. This tunnel was not an original design or anything like that. They actually was built in 1910 by the British National Physical Laboratory, and they operated for quite a while. And some of the higher ups in the NACA organization had to go over to England, and they decided to go ahead and copy this basically and use it for training purposes. This is a side view of it. You can see, whoops. You have an electric motor. You had the 200 horsepower motor here. You had a neck down. The test section's right in here. It's 5-foot diameter, 15-foot diameter entrance. You have a fan blade back here. The interesting thing is, at that time in 1920, when this went into effect, operation, electrical service in the Hampton area was not the greatest. It wasn't a big urban area, and the service was poor. So initially, for the first several years, they borrowed a Air Force Liberty 12-cylinder engine, and they hooked it up and ran a generator, which in turn ran the motor, which in turn turned the blade, which forced the air through. Another indicator that this is an early design is the fact that it was a non-return tunnel. It draw air in, came out, and exhausted Are you hearing some noise?
I'm hearing some background noise. It's the microphone, I think.
Oh. I'm not sure how to fix that. Is that better or worse?
Well, talk some more.
Talk some more, okay. All right, let's see. Okay. Now, in '67, the 50th anniversary of this tunnel, they had the model shop actually build a scale model of it, a fifth scale model. And again, entrance, test section. It's just they didn't have fisheye view, so you really can't, it's hard to get a side view of this thing. This is a view of the entrance cone. You had, it's 15 feet from there to there. And you see all these little, it looks like honeycomb, but it's not really, it's just tubes. The tubes are there to straighten out the airflow. What you're looking for in a tunnel is a nice linear flow, straight flow. Now this view, you see the model in the tunnel, the door is open, it's circular. Another set of cones to straighten out the ears just before it went in. Let me go back a bit. Here, you see up top here, in this part of this room, you have scales, and you also end up scales down here, which the other photo showed. Oops, back. The scale here. And the scales were used to take the measurements, the forces on the airplane when it was being operated in the tunnel. And this is a model of the Cheney. It's a very popular plane back after World War I during the 20s. And that's a side view. There's a front view of it. And you can see even more cones in the background and the four-bladed fan. Okay, now, even though this was a training aid and everything, we were trying to get some good data from it. But what they found out is they were having a good deal of problems because while you're using a one-fifth scale model, they were getting scale effects problems, which were caused by rental numbers, which we're going to talk about next. Osborn Grinnell was born in Bristol, Ireland, and he studied and ended up becoming a professor at University of Manchester in England. His forte, he was an engineer slash physicist. His forte was studying flow of fluids through tubes. And what he found was that at a certain velocity, the flow would be linear, straight, or laminar. But if you increase the flow, you would end up getting a turbulent flow at a certain point. I don't know if you're familiar with, well, if you're all designing, probably you had, when you were younger, you had older relatives and they smoked a lot, and it wouldn't be uncommon for them to put the cigarette down, and if they were indoor, you would see the smoke come straight up for a certain distance, maybe about a foot, and then it would start to spread out, and that would be your transition zone. The earlier part, which was straight, what you would call the laminar or linear flow, and then it would break up into a lot of clouds and turbulent. Same thing happens in a tunnel, wind tunnel, or tubes. And he developed a formula, and this has been, it works for all fluids, and air is a fluid. And it has to obey the laws of fluid dynamics, and this would apply to it. So some of the things have been changed. Air has been put in instead of fluid, but basically Reynolds number is a dimensionless mathematical quantity that varies directly with the size of the body, the velocity of the stream, and the density of the air, inversely with the viscosity of the air. Everybody understands that, right? Okay. I read a lot of information when I'm gathering data for this, and NASA had several good pages. And the best explanation is basically it's a study of similarities. Imagine, if you would, in your mind's eye, you had a real full-scale airplane here, and over here you had regular normal air. Now, But remember, you have three things. You have size, velocity, and density. All right, we're going to put this in wind tunnel. Well, that means the size goes down. So let's say it goes down to 1/20th scale. Now, what are the other things? Is velocity. Well, we can't really change that because we have to go and clip whatever the velocity in the wind tunnel is going to be. So that only leaves its density. And how do we increase the density of the air? Well, there's three ways, but the easiest way, and what they mainly did, was they pressurized it. What you're doing is taking a cubic foot of air and pressurizing it. If you pressurize it down to 20 atmospheres, or 294 psi's, you bring it back down. So now these are similar again. So any information you gather on your model should be relevant to if it was full scale up here. Okay, you follow me? I hope so, because I'm going on. Now, they hired a lot of young aeronautical engineers. They looked around and they were able to hire an experienced engineer. His name was Max Monk. He worked for the German aeronautical concerns during World War I. You had to get him a special waiver to get over here because he was considered at the time, even though this was 1920, having concerns with the enemy. The president at the time had to sign off, but he came in, and while he worked basically on theoretical airfoils and everything, he ended up heading up the department, and his suggestion was, because of these problems with the rental numbers and the similarities, what they were finding with the first tunnel, let's pressurize the tunnel. And so this was bought off, and for $262,000, they were able to authorize it in 1921, and they actually were able to get it in operation in 1922. They were also very lucky because they had a facility really close to them, about 3 miles away. It was the Newport News Shipyard and Dry Dock Company that built battleships during World War I. They built a lot of large transports, things like that, cruisers. So they had no problem with building big boilers. And you can consider this basically a boiler. It was, 15 feet diameter, and it was 34.5 feet long. Empty like this, it weighed 83 tons. So initially, I found two different theories on how they moved these things around, but one of them was the railroad. Well, they moved that around on the railroad here inside the shipyard. The only railroad they had went to Langley at the time could not handle that weight. It was a small railroad. So they ended up putting it on a barge. I'm sorry, most of the times I was able to find rather high resolution photos, but this is any photo that shows it on a barge, and it's not the best resolution. Oops. Yeah, okay. I don't know if you can see it or not. The water line is here, and the barge is there. Finally, they had to take it. It's on Newport News and Hampton and Langley Airfield. Everything's on a peninsula. So they had to go down the James River, come around, and then come back up into the back river and dock. Now, I do not know how they got that thing off the barge, but somehow or another must have, because they got them on these big timbers. That raises the other question, how they moved it, and no one knows. They could have done it by manpower, I don't know. The mechanical means were probably limited at the time. Whatever you had to be careful, because at 83 tons, you didn't want to get that into motion, because that would be very hard to stop. But somehow or another, they got it into this building, which ended up being building 60A, which is next door to the first wind tunnel. This is a picture of Dr. Monk with his creation over here. Now, to get to 20 atmospheres, or 294 psi's, they couldn't do it with one compressor. They had to do it with 5 compressors, all done in staging. The first one would do it to a certain point, let's say 5 pounds, the next one would do it from 5 atmospheres, next one 10, on and on. until they got 20. And then they could pipe it into the vessel. Now eventually, a short while later, they were able to put basically a deck around it. This is the entrance hatch. That's the only way of getting in and out of that thing. It's 36 inches wide. They had to build the tunnel inside that. And when they did that, it actually brought the weight up another 2 tons. You've got observers here, and you've got the control panel here. This is a good side view drawing. Basically, it's continuous and annular flow. In other words, the fan is here, it's drawing air this way, it comes up and around and back again. But being circular, it's all the way around, circulating. And you can see a model here, and you got a scale up here. You have a 250 horsepower electric motor here. This is several things on this photo. You have the model, but you also notice the wood. That's how they built the inside of that tunnel, basically wood. You have a screen to catch any, hopefully this would not come off, because they didn't want to hurt the propeller. Now, these models, because it was in a pressurized tunnel and it could go up to 20 atmospheres, it could not be made of wood, because wood is fibrous, and at under 294 pounds per square inch, it would just crush that wood. So all these models had to be made out of metal, which back then wasn't the easiest thing to do. Here we have an engineer doing some adjustments down here. And this is what they call a 2D airfoil. It's basically airfoil here. It's the same here. It's all the way across the same. And they can change the air wind velocity and get different readings on it. And what they're trying to do, and what the main purpose of this tunnel is to try to develop a whole series, a whole family of airfoils that they could then publish the information, and American aircraft manufacturers can then use to develop more efficient airplanes. I think the first technical manual that came out was probably about 1930 with this information. It took them a long time, as you can imagine, a lot of different airfoils and a lot of different runs, because what they would do is they would run this tunnel up to 20 psi, 20 atmospheres. All the runs they want on that one particular airfoil, then they would drop it down to 15 psi, repeat all those runs, and go down to 10 psi, atmospheres. Keep it here, down to 5, down to 0. And that way, not only did they get all that data, but they could figure out any formula for other tunnels that if you're working with different pressures, that they could correlate it up to full scale. Now, young engineers were in demand because they had good sharp eyes and they could see those scale measurements. So that's what they were doing over here. I was part of their training. Now, let's go back. The variable density tunnel, as it was called, turned out to be a milestone for NACA. They basically put it on the map. No other tunnel had this, was operating with this temper pressure in the world. After they started operating, maybe about 5 or 6 years later, afterwards, the Europeans started building pressurized wind tunnels too. So for that period, this was the only way you could do it, or the only one who had that information. Now the tunnel itself kept on being in operation until in the early 40s, but the use of it as a wind tunnel per se declined as more larger and better tunnels became online. However, they did not waste anything. So even though the use of the variable density tunnel declined, they still found a use for it. They used it as a pressure vessel. You could pump it up to 20 atmospheres, and then this is 11-inch blow. Whoops. Yeah, this is 11-inch blowdown tunnel. And
What?
blowdown tunnel, I'll tell you. Basically, if you can imagine, I didn't bring my prop, but if you had a tube, okay, and you brought a line down from the variable density tunnel and brought it up this way and let the air flow out, it would suck up air in from the bottom. And for this came into effect in 1928. They were getting 0.9 on a Mach. They were getting at ground level, which this is, they were getting about 700 miles an hour, which was unheard of at the time for wind tunnel doing testing. What they were looking for, what actually prompted this use was airfoils. Land speed records at the time, in 1920 it was 176 miles an hour. By the time this tunnel came online, it was already up to 297 miles an hour. Now granted, that wasn't every ordinary planes, but it wouldn't take an engineer much imagination to figure out that the speed of airplanes are going to go up and up. And the propeller actually operates at a higher speed than the airplane, especially at the tip when it's going around and around. So if you're at 297 miles an hour, you're probably getting into low Mach, no, I'm not going to say low Mach numbers, but you would be getting into the order of 0.7 for Mach. At that point, you get a lot of shock waves, a loss of efficiencies, drag, so your propeller doesn't become as efficient. So one of the big things they learned on this tunnel was the fact that thin airfoils operated much better at high speeds than the thick airfoils that they were using on wings. So our propeller manufacturers started using that information and started making the tips of the airplanes much thinner airfoils. So when in the later 30s, when airplanes started operating more and more in the 300 miles an hour range, and your wingtips were getting into the Mach, getting close to Mach 1, they released more efficient. One interesting side note about this tunnel, in 1928 November, Amelia Earhart visited Langley Field, and they showed her around the Air Force, Army Air Service part, but she also came over to the NACA Division. They showed her some of the tunnels. They showed her the 11-inch high-speed tunnel, and they actually operated it for her. And being November, she was wearing a nice raccoon coat. You're getting it, okay. So, she's somewhat a distance away from it. And again, remember, it really sucks up the air at the bottom. Well, she wanted a closer look. So she came a little closer, and then a little closer, and next thing she knew, her raccoon coat got stuck. Getting stuck. Luckily, some of the people around her grabbed her and pulled her back. It did tear her coat, though, but you have to be careful with those things. They also wanted you to get a larger, this is a 24-inch blowdown tunnel. It's all on the outside and back of the building, so they could pipe in the high velocity. This was even, you could put even larger airfoils in this than you could the other one. This one actually kept on operating until 1953. In fact, 1953, they were no longer, by then they were no longer operating the variable density tunnel as a tunnel per se. It was strictly a pressure vessel. So in 53, it had to get certified as a pressure vessel, and it was. And then in 83, it had to be recertified. But at that point, NASA headquarters said, let's not. I mean, this thing is pretty old. It's made a lap construction of boilerplate steel, of which was 2 1/8 inch thick, I might add. They just didn't trust it anymore. So they basically decommissioned it. And in 1989, they decided to move it. So the only way to get that thing out of the building was to tear off the roof and lift it up and then they put it on a big flatbed. And this is all on Langley Field proper, which in NACA they always consider it as East NASA, or East NACA. And it was being moved over now to the newer section, which is across the airfield, and it's called the West Side, or West. It's being put by the conference center in a nice shady spot, well painted, well taken care of, and it's still there today. Okay. All right, but we weren't done with propellers yet, because basically model testing of propellers was found to be inadequate and the information did not conform to full-scale experience. So again, Dr. Monk made a proposition that they made a bigger tunnel, that they could put a full-size propeller, full-size engine, full-size fuselage in, and test it. So remember the three things you could change? In this case, they're not changing the density, and they're not changing the velocity, but they are changing size. They're going with full-scale size aircraft and parts. Now, this tunnel would cost $291,000, was authorized in 25, and became operational in 27. And you'll see this in the next, in a couple more tunnels, but they basically built the metal frame, and then they put sheeting on the inside, because that would be part of the tunnel wall, and the metal frame would be on the outside. Now the sheeting is made out of 2x6 ton, tongue and groove pine sheeting. So that's, but that back then, that 2 inches was 2 inches. And 6 inches was 6 inches. Not like nowadays. This is a rear view. Oh, this tunnel was 166 feet long, 89 feet wide, and the height varied from 50 to 56 feet high from the ground level. And it had we got some 3-view drawings. Up here, it's 20 foot here, 20 foot. It's a circular entrance column, and it's 30 feet from the entrance to the exit column. You got a single propeller here, driven by 2 diesel engines here, and we'll talk about that shortly. But the flow is here, and it flows around, and here, and it flows around. Basically what it's going is going like this, continuously. You like continuous flow because once you get that massive air moving, it takes a load off the electric motor, or in this case the diesel motors. Same thing happens with cars. If you're driving at 70 miles an hour, you spend all your energy getting up there. You don't need all 8 cylinders or 6 cylinders to keep it going. And some cars are equipped with computers that will actually turn off some of the cylinders. Once you've got that mass and everything moving, it will stay there for a while. Okay. Now, because of unreliability of electric power and everything, they decided to use some diesel engines from the T2 sub. They only made 2 of these. They were supposed to cruise with the fleet, but they had problems with the engines because they were linked in parallel in pairs, and they just didn't have the electronic capability of keeping the 2 engines in sync. So it was always out of sync, and it was a mess. So it had a very short life. They decommissioned it, and it sat over in Norfolk, which is across the water from Hampton. And they were able to get 2 of these engines. And yes, they are big. You can see a man right here. They're huge. They're 1,000 horsepower, man diesels, that's manufactured, AMD. They're 6-cylinder, 4-cycle, and they run at 375 PSI. So they got them staged together. They ended up building a shed. And what they did is put it on a pulley with belts and came up here and they showed it to the propeller shaft and would turn the propeller. They were able to get it that model up to 110 miles an hour. Here's another view. You can see how small people are compared to those engines. They ran those things for 6 years until the Air Force started complaining quite a bit because the airmen were complaining because it was so loud noise they couldn't get to sleep sometimes at night. So they were finally able to get some electric motors and put them in place of here. Whoops. Okay. They used aluminum. I'll get used to this better than last time. They had aluminum blades. They're just about 28 feet in diameter. Okay. Now, they basically, interior construction for these things, basically like I-beams here, but then they would put wood in between, and then they would fair or sand smooth the inside, and you could leave outer skins was somewhat rough, it didn't matter. And here's this Fairchild airplane. You can see it's full size with the wheels and a little small cowling on the engine. And these struts are holding it. They're sitting on top of a floating frame, and your balances are down below. This is a drawing of it. And you can see, oops, you can see some of the scales. There's another set of scales here, but somewhere along the line, it got whited out. That's the best I could find. And you have one scale here, another scale here, another scale here. You have 4 scales here. What they would do is, this fellow was measuring drag at a certain point, at a certain time speed and angle was achieved. He would call out drag 55 pounds. The recorder would write that down, and if this fellow was measuring lift, he would say lift 63 pounds, and the recorder would measure it. We gather all the data, and then it would take a while to process it, because they didn't have any type of computers back then. Now, one of the things early on they found was that you got a lot of drag out of your exposed landing gear. Now, aeronautics engineers weren't stupid. They knew they were getting drag, they just didn't know how much. But from the tests here, in these tunnels, what they found out is this is causing up to 60% of your fuselage drag, which is quite a bit. And what you'll note is in the early 30s and on up, there's more and more reliance on retractable landing gears. Once they found out it caused that much drag, they decided they had to do something about it. Another thing they worked on is the same location with the same airplane. The airplanes that day relied heavily on radial engines, which were air-cooled. The airstream would flow through the little fins and dissipate heat. Well, that also caused a lot of drag. These also contributed up to 30% drag. And so NAC developed cowlings that would enclose the radial engine. But they had to have baffles inside, little plates to channel that inflow air to each cylinder. Because you didn't want the cylinders to overheat, that wouldn't do any good. You had to be able to cool the engine as well as reduce the drag. And these are a handy-dandy metal shop who are making and forming the cowlings. This is a little slide that NACA put out. It's got some good information. Again, you can see the radial engine and all the turbulent flow developed from that, and that develops drag, high drag. An engine would have to go to 266 horsepower to move it at 200 miles an hour. But when you put on an AC cowling, this is a little cut view through so you can see it, that the whole thing would be one solid piece. You only needed 160 horsepower to get 200 miles an hour. So you became much more efficient. You could go faster, you could get better miles per gallon. Now this is the same airplane. Here, it's got a regular uncowled radial engine, Over here, it's got an NACA cowling engine. And as it says, the best this plane could do is 118 miles an hour. Over here, with the cowl, it can now do 137 miles an hour. This kind of piqued the interest of the military. They were interested in speed. So they became developing this more and more. Another thing I don't really have a picture of, which they used to help aircraft manufacturers, so they found out they were doing studies on the best location of airplanes at this time. Some of them, the bigger transports, had like 3 engines, one on the nose and 2 below the wings. And so they actually mounted some in the tunnel and did some tests. And they found out, even though you put a cowling on those engines under the wing, you still had a lot of drag and interference with the airfoil that was above it. So they played around, they moved it further up, down, all different locations. They found that the best location, if this was like the leading edge of the wing, the best location for the cowling would be right in the center. Not high, not low, but right in the center of it. And if you look at the transports that were built in the mid-30s and later, that's what they all went to. Boeing 247, your DC-2s, DC-3s, they're all good examples of that. They have cowled engines, they're in the middle of the wing, they have retractable landing gears, all the things that were developed thanks to this one particular tunnel. And this one actually, this particular tunnel stayed, oh yes, I'll talk about that too. I know. Robert Collier created the Collier Trophy in 1911, and it was to be given annually for the best achievement in aviation for that year. In 1929, NACA was given the Collier Trophy for developing drag-reducing cowling for the radial air-cooled engines. And that was a nice little feather in their cap. They were proud of that. So, we're going to take a break now. Thank you.
Thank you all for taking your seats, and we will continue. Hasn't this been interesting?
Yes.
And for those of you who are having a little bit of a hard time hearing, we're going to try and experiment with Ben has moved the microphone closer to his mouth, so let us know afterwards if it helps. We're trying. Ben.
Okay. How's that? I know it sounds louder. Worse?
That's worse.
Okay. How's that? Better?
Yeah.
Okay. How's it in the back, though? Okay. All right, we're next going to talk about the full-scale tunnel. That lasted for quite a while, over 70 years, and a lot of things happened to them. A lot of good things happened to them. Okay. Now, as big as you thought the propeller research tunnel was, this thing is gigantic. It was 434 feet long this way. It was 222 feet this way, and it was 97 feet here. The footprint was 2.4 acres. I thought you'd catch that, yeah. Now, this view is of Langley Field in 34. And you can see some of the airplane hangars and things like that. Here's a full-scale tunnel here. And this is a blow-up of that section. This is the propeller research tunnel. You could almost put 4 of those things inside here. That's how big that thing was. This is the back river. Let's go back here. That I've talked about. This is the back river here. Goes around here, goes around here, up. Again, they did a metal structure. Oh, I might add, this is all after they've done a lot of piling work. What I mean is they drill a hole, put a pipe in, put concrete in, till they get bedrock, because you're 3 feet above the back river there, and you're really close to it. So anywhere in the peninsula, you have no basements. Because you dig deep enough, you're going to hit water. So everything, all these big buildings are built on pilings. Oops, wrong one. There we go. And again, they sheathed it with panels, except they didn't use wood. For whatever reason, they went with walls and roof covered with corrugated cement asbestos sheets. Yeah, well, back then it was good stuff. 5/16 thick, 42 inches wide, and 62 inches long. And it took quite a bit of them to do it. Now, this tunnel ended up costing $900,000. It was authorized in February 1929. And it became operational in May of 31. Now, it didn't get all $900,000 at once. Congress doesn't do that. I think they got $500,000 initial payment, and the other section was broken down into 2 other payments. But one good thing with the Depression, if you want to look at it that way, is that they were able to get cheaper manpower. Contractors put in lower bids because they needed the work. So if they didn't have that factor, it probably would end up costing a bit more. This is always a fun photograph. This is the entrance cone where the air comes in, and it's 30 feet here, and it's 60 feet here, and you see a fella standing here. There's another guy up there. I love it because I'm thinking, wow, OSHA would have a field day today with the wooden ladder. Now, this is inside the entrance cone. Well, the entrance cone is right here, and they're doing some float work. This is their scaffolding. You can see how tall this fellow is here. Oh yeah, it's big. It's big. Now, that photograph was probably taken around this area right about here. Because you just see the edge of here, you can see the edge here, somewhere in this area. Again, it's very similar to the propeller research tunnel in the fact that the air comes here, channels around, goes around. Same thing on this side, comes up here. It's 60 feet here. It's 30 feet high, and it's basically 50 feet between the lips of the exit cone and the entrance cone. It has 2 electric motors. These are 4,000 horsepower electric motors. This is a photograph of them pouring the foundation for the balance room, or the balance house, depending on how you want to call it. Here it is, all the Toledo scales, same framework, pretty much similar to what was done in propeller research tunnel, except larger. Now this was the, as it says, the first airplane tested in full-scale tunnel in May of 31. It's a Navy Vought plane, and basically it's an observation airplane. Now, it's a little out of sequence, but what you can see is all the metal I-beams that were used to make the lid. And what's also, what I thought was interesting, is right here, going down to pilings and then down bedrock, where the engine mounts. And you actually see where the airflow would split right here, going around. And here are your, initially it was equipped with aluminum propellers. And here's your mounts. There's your nacelle and electric motors inside. Interesting thing, in 37, the 8-foot high-speed tunnel, they had aluminum blades, but they suffered a major breakdown. The blades had metal fatigue and they all tore up. So after that, they started looking really hard at all the other metal blades they had in tunnels. And they decided to replace these with wood ones. So they went over to the wood shop, model shop, pattern makers, whatever you want to call us, them, and they ended up making them by hand. And the nice thing, these blades were put in the tunnel in 38, pardon me, and they were still in there when they tore down the tunnel in 2011. The same set of wood blades. I always like isometric views, they're fun. You can see so much. Oops. Okay.
What wood did they use?
Spruce. Spruce. Yes. Let's see. Yeah, you can see the cells, the blades, the balance house, the model, the reduction. The sidewalls, where the air flowed back and forth, was 50 feet wide, and they would vary from 70-some feet here down to about 46 feet here. Up till after the war, they actually had skylights, 30-foot by 40-foot skylights up above the test area to get some light. And they would move, they had two large doors here and here that could open, and your models could be rolled in, and the cranes would lift them up and put them onto the struts. It's back in 36, Grumman, F-3F. This was the last biplane fighter for the Navy, but they were doing some tests on them even then. It's probably drag. Now, this is a Corsair. They're doing drag tests. When World War II came, this tunnel went on 24/7. It operated 24 hours a day, 7 days a week. They did that for 4 years. And if you think about it, you run the numbers, they're basically in those 4 years did 16 years worth of work with 3 shifts. But every plane that the Army Air Corps, Navy had, especially fighters, went through these drag reduction tests. Basically what they want to do is start it out with a perfectly clean airplane. So what they would do is they'd take off the propeller, they would make a wooden cone, attach it, and then they would put tape over every gap, everywhere. This is side view, top view. Same thing on the bottom. They would tape everything. Then, once they got all the data for a clean airplane, they would maybe untape the aileron and then run tests on that. Basically, they were going to come down with a shopping list of parts that they could give the manufacturer. So if you eliminated the gap here or changed this here, you would save so much drag. On average, they would speed up the aircraft 25 to 50 miles an hour. Now, initially you don't think that's very much, but in combat, when you have aircraft that are very similar, that extra little miles per hour can make a difference. In the military, like I said, I think they did over 150 different airplanes, these drag reduction tests. Now they still were able to do some basic research. Okay. Oh, here's a Curtis B-40. This was actually put in before the war, but it was one of the early prototypes. So they were getting some tests run on that. Again, same thing. This is a YP, which is a pre-production. And if you notice the date, yeah, December 11, 1941. So they already started. This is a Mustang, P-51B. It's a different shop. Again, you can see they took the tapes down here, and they already took off the propellers. This is later in the war. This is a Bearcat. This is what they developed this airplane for, was to try to. It was very fast, had very good climbing. It was, and they were going to try to build these things to take on the Japanese kamikazes. But the war ended too soon. Or soon didn't soon enough. This is an interesting airplane. It was made by Alexander Lippisch, who's a German, and he was very much into delta wings. And he was going to try to make a fighter out of this for the Germans by putting ramjets underneath there. But that never came to pass. This was the only thing that was built, just a glider, because they wanted to do some low-speed tests. The only way they could do that was with gliders. So at the end of the war, they had a delegation of NACA officials go over and pick out things that they wanted to bring back and test, and this was one of them. Because NACA was very interested in delta wings. And in 46, they put it into the full-scale tunnel. And it was in there for several months. Let's go back. I want to point out, it's got a very large radius on the leading edge here. You can see it here. The same thing on the other side. They had very large gaps between the wing and the ailerons back there. What they found out were the large radius and the large gaps did a lot to make airflow separation up here and back here and cause more drag. It did not get as much lift as they thought it would. So then they decided to play around a little bit with it, since no one was going to complain. They basically took off the whole vertical tail. They put on an F80 canopy here and a much smaller little rudder back here. They made extensions on the leading edge. So basically it went from a round leading edge to a much sharper leading edge. And by doing that, they got they improved the flow over the wing, and they got that type of lift that they were looking for. And this would eventually lead to the whole series of delta wing fighters made by Convair, who happened to hire Dr. Lippisch in their late 40s. They made a XP-82, which never went into production, but they did make the F-102 and F-106. Now, lest you think only airplanes are tested in the wind tunnel, that's a submarine. It's the, as you can read, it's the USS Elbecourt. It was a nuclear-powered research sub. This is the 1/5 scale. Now, the Navy has a lot of test facilities, and one of them up is the David Taylor water basin up in D.C., where they test in water the various ships and subs. But they could not get a large enough scale because what they were trying to find out is how much drag would be coming from all these vents. You're basically your flood and vent holes. And so they put it in a full scale tunnel. They tested it, and the researchers told them you're getting about 60% of your drag from these holes. So they ended up reconfiguring them, and they got it better. This was launched in August of '53 and decommissioned in December of '72, the full-scale one. Now, that's a B-58. This is actually an XB-58. This is a free flight model, because one of the things they developed in the '50s was actually flying models inside the wind tunnel. The wind tunnel is so huge. You get cable. One of the cables would be a safety cable. The other one would control electric motors that run air control surfaces. And the third cable would actually hold compressed air that could come out jets here. Now, your tunnel would go to 100 miles an hour, plus the thrust off the compressed air allowed the plane to fly. You can see people here down here looking at it. I don't know whether I want to do that or not. If these things get away from me, it could be rather nasty. You had a roll and yaw pilot here. Roll would be like that, and yaw would be like this, going back and forth. And then you had a pitch pilot here, which would be going up and down. So those two pilots basically flew the airplane, hopefully together. You had a power operator who controlled the flow of the compressed air through the engines, and the most important person was the safety cable operator. You could either let it down or pull it up, depending on which way was the best. Oops. And that's just a photograph, basically the same thing. This is another free flight. This was the HL10 model. It's a lift and body. Back in the late 60s, early 70s, they made HL10, they made X24, they made M2F2. They're all different variations on a lifting body. You don't have a wing. Basically, you had a flat bottom or a round bottom, but you're just flying it, coming back, let's say, from space at a high angle of attack. and getting their lift like that. This work here helped a lot later on with the shuttle, because it was basically doing the same thing. Same model, but this, well, not the same model, same type of airplane. It's a much larger, but you can see the flat bottom here, and it's got a round top up here. There's the HL10 again. Now we got something without wings that flies. This is the LLTV. This was to simulate lunar flight, but in the Earth, actually landing, I should say, because there it is flying at Edwards. What you basically had was a jet engine here, and you had tanks that held hydrogen peroxide, you had rockets underneath here, and you had regular you didn't have airfoils, you just had smaller rockets to pitch and yaw and roll. Whoops, I'm getting ahead of myself. All the pilots, all the commanders who landed on the moon were trained in these. And every one of them agreed that this was the most accurate simulation that they ever had. Because what they did is they'd take up to 500 feet, 1,000 feet, they would then throttle back the rocket, the jet engine, so it simulated lunar gravity and would start going down. Then they had to operate the hydrogen peroxide rockets to stop that drop and to slowly descend and move around just like they would with a limb. It wasn't the easiest thing to fly. They eventually made 5 of these, and they lost 3 of them. Now, this is an interesting story. We had a 106 out at Langley Field, and they flew it several different configurations. But one of the last ones, they wanted to do vortex generator, vortex flaps on the leading edge, and they wanted to test it. But they were able to obtain a scrap, basically 106, and so they started to cut it in half, because they're going to make a semi-span model, which is half a fuselage or wing you could put in the wind tunnel. And Fabrication Division has a certain sense of humor, so they just started to call it the Model 53, because it's half a 106. As you can see, you got a fellow down here, he's doing some cutting, and there's some cutting up there. And when they got that much cut in half, they got some temporary braces in. They've got all one side cut off here now. Whoops, darn it. Fab shop did a lot of work here, the machine shop did, and what we ended up doing in the model shop is they did not want to cut the plexiglass canopy in half, so we ended up making a wooden one and a little wooden nose part. But every group that worked on this project got to stand in front of it and have their picture taken. And there I am. Yeah. But that's what I mean by a semi-span model. It's half a fuselage with a full wing. Whoops. Yeah, all right. Full wing. And these are the new flaps that we're putting on, testing. This would be the last NAC, actually by then it was NASA model test done in the full-scale tunnel. This is the F-22. The tunnel was getting old. It was costing a lot of money to maintain it and to keep it up. So they basically decommissioned it in 1995. But that's not the end of the story. ODU, Old Dominion University, which is over in Norfolk, has a good engineering curriculum and everything. So they wanted to use the facility. So it took a little while, being commercial and government, or academic and government, to work out the paperwork. But in 1996, basically the end of the full-scale tunnel was handed over to ODU to be used. While the initial contract stated that it couldn't use test airplanes, everything else was open. And they found that testing race cars was very lucrative and the service was in much demand. they were getting $1,200 to $1,500 an hour to test these. And they were usually tested for 30 to 40 hours each. So in 4 years, they were able to pay off the loan that they had to take out to bring the tunnel back up to life and up to date. But NASA wasn't really that hard on them. It was about testing airplanes, depending on the airplane. There was a project called the Wright Experience that back in the early, well, started I think in '99, but what they wanted to do was make an exact replica, duplicate of the different Wright aircraft. What you see here is the 1902 glider. Oops. No. And I superimposed a picture of Orville. And this was tested in 2002. And then the full flyer was tested in 2003. After this, they actually took it down to Kitty Hawk, and in December of 2003, they actually flew it at the 100th anniversary. And this would turn out to be the last test in the full-scale tunnel by ODU. NASA needed to test this aircraft. They didn't have the facility to do it, so they went to ODU and ended up testing it in their old previous tunnel. I thought that was cool. It's the, whoops, it's the X-48B. It's basically a blended wing body. And you're familiar with regular transports today when we fly on them. They're basically circular. Blended wing body stretches out the sides and everything and blends it right into the wing. So you really don't see a fuselage per se. It's all blended in here. This model is 20-some feet wide, weighed about 540 pounds. They had 2 engines, because what they're going to do is after these low-speed tests here, they're going to take it out at Edwards and fly it as a radio-controlled airplane. But they wanted to get some low-speed data on it first. But all good things come to an end. This test was done in 2009, and ODU basically is finding it harder and harder to keep it going, so they gave it back to NASA. And in 2011, came the wrecking crew. And they tore it down after 70-some odd years of its faithful service. Okay, that's the full-scale tunnel, which was very important for several reasons. But now we're going to come to another little tunnel. It's a 20-foot spin tunnel, and this also, even though it's small, a lot smaller than the full-scale tunnel, was a very important tunnel. It had a 12-sided base. You really can't see it that well. You can see the back river over here, though. It's 63 feet from flat to flat, and what you see in this photograph is the interior wall. This would end up being the exterior wall. And this is where it's been finished, even later, but you get the idea what it looked like. Now you can see what's going on in the inside. This tunnel was actually, considering everything else, was built on the cheap. It only cost $100,000. It was authorized in March of '39 and operational in March of '41. You have the fan blade up top, and it blows the air up, goes through the training vanes, come down, goes around. It's annual. It's a circuit, well, 12-sided, but roughly a circle, so the air is continually going around, constantly all the way around. And let me go back. You've got cameras, you've got a model here, you've got cameras down here, but you also have a net. What they were looking at, or what the Air Force would tell you, is that 10% of all military aircraft accidents and 25% of all fatalities are attributed to stall and spin accidents. Basically what happens is when the aircraft stalls, it loses its lift and it drops. And not always, but a lot of times when it drops, it will go into a flat spin. Sort of like what a Frisbee does. It's going around and around. And unless you know what kind of controls, you may have to work the ailerons, you have to work the rotors in certain directions. Unless you know what to do, you may not be able to get out of that spin. So if you're low, the only choice you have is to eject. But if you're higher up, you can do these recovery maneuvers, get out of the spin, and land the aircraft, hopefully. So this whole tunnel was dedicated to figure out how to get that particular airplane that they were testing at the time out of the spins. They also tested spacecraft too. Here's a Mercury spacecraft, but they were actually working with drone chutes. Now, what you see here is a researcher, a cameraman, and one of the tunnel technicians, and he has just finished launching a spin model into it. And you basically stand at the open window and you toss it in like a Frisbee. You just snap your wrist, toss it like that. And you have another man, it's not pictured in there, but he operates the fan. And he'll bring the fan up, bring more air up, so it lifts this flat spinning aircraft up, model up, I should say. Full-scale tunnel, spin tunnel. Eventually they got an office. They always need offices. This is a nice photograph. What you have here is an F4 in a spin, but it's time-lapsed. So what you can see is when it initially went up, you got brought it back down, and he's spinning around. The interesting thing is this tunnel has copper wires all around that test area on the inner side of the tunnel. And inside the model, I never could find a good picture of it. Inside the model is what's called a mousetrap. And basically, like a mousetrap, it would go down like that. So they push the spring down on it, have a latch, and then they attach wires, and these wires will go to the different control surfaces. And they'll set it so if this magnetic field comes on, if you put power to your copper coils, you're going to get a magnetic field. And that's going to let that little latch loose, and it's going to spring up like that, and that will pull the wires and change your settings. As you can imagine, they have to go through it quite a lot until they find out the right combinations. And once they do, then they can go to the Air Force and say, hey, look, if you want to get your F4 out of a spin, this is what you have to do. During World War II and up to today, every fighter, light bomber, attack aircraft, trainers, everything goes through the spin tunnel. They're all tested, and they all have to work out how to get out of the spin. And this includes secret models, secret aircraft. Everything has to go through this tunnel. And I want to stop on this note. It's a nice little picture. It's from the bottom through the net. And you can see the model up here. You got the observation windows here. And of course the net. So, we're open for questions.
Was that very noisy in there?
No, I've been in there when they ran. It's not that bad, especially when one of the windows, with the windows closed, and when the windows are open, or when one of the windows is open, it's more drafty than noisy. You, ma'am.
What is your training, and how did you happen to end up at NASA?
Okay. Sorry. What was my training and how did I end up at NASA? Okay. When I went in the Air Force in 1970, they give you a choice of what you want to try to become. I picked several different things, but I only got my third choice, which was, as the Air Force called it, was a metal processing specialist, and which actually turned out to be a welder. So I was taught how to gas weld, arc weld, TIG weld, and when I got out of the service, that's what I did for a few years. But one nice thing in being in the service and being a lone man on the totem pole in our shop was I got put on second shift. And our shop was one of those old hangars. Basically, we were at one end, then you had the machine shop, you had fab shop, and then you had paint shop. So everybody on second shift was pretty young, minor grades. So some guys would say, teach me how to weld. I said, okay, you show me how to run a lathe, or a milling machine, or sheet brakes and shears and rollers. So by the time I got out of service, I could do all those things. But I couldn't really find a job to handle all that, so I just basically got a good job at Howmet, which was TIG welding vanes for turbines that ran electric power hydro manufacturing vanes, cobalt alloy, nickel alloys, and things like that. But anyway, my wife happened to be working as a contractor at NASA, and she was able to spot a little ad that they were looking for apprentices. You know, they had an apprentice program for quite a few years, so they start to open it up. And so I applied, and in '78 I was hired. The three of us that were hired for the model shop, we were all older and probably had more experience, because up till then, the trainees that they hired were basically right out of high school, didn't know anything. So they basically had to be taught everything. So when they got us, it was like, oh, what do we do with these guys? They already know a lot. Basically you start working, making small parts for the airplanes, these models. You might be tasked to make horizontals or a vertical tail or something like that. Then later, if they got more confidence in you, you might end up start making wings or fuselage. And then after a couple more years, you might actually lead jobs. I think that covers it. Great.
Then those early models, prior to the free flight models, were all appeared to be in straight and level flight. Was it thought unnecessary to test other attitudes or banks or things like that?
Was it necessary to test the airplanes and other attitudes rather than straight and level like a lot of those things showed? I think what you were looking at there was just the testing done on the drag and drag reduction, and for that they kept them at straight and levels. If they were coming in for more basic research on, let's say they're having some prototype, different aircraft, they might put those into different attitudes, yes.
So those struts were somehow you could maneuver models around, or you had to do that?
No, you could maneuver them around. Yeah. You could shorten one, change the pitch. You could, on the two side ones, the front, you could make it yaw. Things like that. Gene?
On a variable density tunnel, those balances that were in there, or the scales, it seems to me hard to make those work when you got a 100-mile wind going past them. How do those work?
Don't know. Sorry. How did they make the scales, the balances work in a wind tunnel when you've got 100-mile-an-hour winds going, especially a variable density tunnel? Don't know. They might have been shielded, that portion, because that was actually above the wind tunnel part. It was connected to the model with cables or rods. So they probably weren't necessarily in the wind stream, come to think of it.
And probably they were tension balances rather than actual weight balances.
Were they tension balances or actual weight balances? I think they were both. I mean, at one point there were one and then they switched over.
If there were a weight balance, you'd have to have some way to get in there and move the weights in order to tell. So it has to be
tension,
something
yeah.
that you didn't have to get in there.
Back in the, it was in the sometime in the mid-40s to later 40s and early 50s, they basically did away with that type of systems, the balance systems. They went to, they still called them balances, but basically they were strain gauge balances. Basically you had a block, you cut slots, you put a strain gauge on top of that, and basically any change in a wire changes its resistance, and you can measure that, you can gauge it. So that's the way we'll do it then. George?
Well, particularly as you were showing those early tunnels, was the federal government strongly behind, were they recognizing how far we were behind and needed to put money into these tests, or was it difficult to get the funding?
A little of both. A little of both. It's just, oh, yeah. Let's see now. So, was the funding easy to get from the federal government, basically what you're saying?
That's right.
Early on. Early on, yes. Initially, yes, more so than, it was harder somewhat in the Depression. Although there were some tunnels that were still built in during that period. They were done with the WPA funds. Okay. Oh, Jim.
In the age before electronic computers, how did they store the data?
How did they store the data before they had electronic computers? Paper. Reams and reams of paper.
Thousands of trees.
Thousands of trees. Gene.
I wondered if you could explain what that Reynolds number means. Is that a empirical measure of turbulence?
Basically, basically it will tell you probability-wise where you were most likely to have turbulence.
Some of those jobs look really, really dangerous. Was there a lot of accidents that happened
The only,
time you worked there?
were there any accidents in the construction of the
That's
tunnels?
right.
And going through all the paperwork and everything, I only found one accident, fatal accident, and that was on the full-scale tunnel. A fellow was up the top, and he made a misstep, but that was the only one. Now, that's not to say that, there were others, but that's the only one I could find. There's, on your handouts, on the 4th page, you'll see a website. That's where I got the majority of my pictures and information from. So if you have any more desires to look into that, I would highly recommend that site. And next week, we'll be talking about 5 more tunnels.
Ben, thank you very much. I think I speak for all of us that you enlightened us beyond our expectations. I had no idea. Anyway, be sure to come back next week for the second half of this fascinating subject. Before you leave, remember to turn off your T-coil and get out your cell phones again. Thank you all. We'll see you next week.
What were you doing it?